Chapter 11, Chemistry in Context, 9th edition. We will be talking about nutrition in this chapter. What are the components of food, and what are their effects on our health? What practical information can we glean from food labels? And there is a lot of information we can get from the food package. We'll talk about how we look at those. How safe is our food supply? We will talk probably not that much about that topic, but we'll mention a few things. What are the environmental implications of agricultural practices, because they do have an impact on the environment and the carbon and nitrogen cycles. Let's see. How do we feed our hungry and expanding world population? We won't talk much about that at all. We will mention it occasionally. Okay? Here are calories. Let's talk about calories. Calories, this is something we've had before. Remember, calories are often used to express energy released when food is metabolized. So when food is metabolized, we talk about it in terms of calories. But how scientists talk about calories and how dietitians talk about calories tend to be different. So note the bottom of this slide. 1 kilocalorie is 1,000 calories. That's scientifically, which is 1 calorie for a dietary calorie or food calorie. So when you say 1 calorie when you're talking about food, you're really saying 1 kilocalorie when scientists talk about it, which is 1,000 calories. And so this gives you an idea of how many joules it is. So 1 calorie is 4.184 joules here. So when you talk about I went to the gym and I worked off 100 calories, okay, that's 100 kilocalories. Follow? All right, so be aware of that. All right, or 100,000 scientific calories. All right, so we like for you to be aware of that. That dietitians and scientists, other scientists, talk about these slightly different. And these are the conversions. 1 kilocalorie equals 1,000 calories, which equals 1 dietary calorie. On this slide, we talk about we are what we eat. And so on this slide, we look at some of the foods that we eat and that we enjoy, and what percentage of these contribute to what groups and areas of food, right? So we have water, fat, carbohydrates, and proteins, and you're going to see that repeated a lot. So for a lot of dietary information we're going to talk about involves water, fat, carbohydrates, proteins. Okay, so that's what you're going to see. And so we just take a look at this slide, and we notice a white bread has water, 37%, almost a third water. And the carbs are pretty high, 48%. Almost 50% of it's carbs. And we have a little bit of protein and a little fat. 2% milk is almost 90%. It's 89% water. Okay, so if you drink 2% milk, you're drinking mostly water. That's how it is. Okay, so when at 89% water, putting 2% milk on your frosted flakes, you might as well just run under the faucet, get your water, wet the flakes, and go ahead and eat it. Get it over with. It's mostly water. What's the big deal? Except you kind of like the little bit of taste that comes with it, don't you? Yeah, the 2% fat tastes pretty good. Okay, so you get it? Well, maybe you would do that. Chocolate chip cookies, 23% fat and 69% carbs. So a lot of carbs in a chocolate chip cookie, but boy, do they taste good. Peanut butter, 50% fat. So yeah, you eat peanut butter, you're getting a fair amount of fat, and the low fat's a little bit better than the regular, but you're still getting a fair amount. And you have your carbs, your proteins. Sirloin steak, a lot of water. So you can go out to the expensive restaurant, you're buying 57% water with that steak. All right, you got it. So next time they offer you a little small steak, take it, soak it in water. Maybe it'll absorb a little bit. Okay. You guys don't like any of my suggestions okay. Anyway, you get the point I'm trying to make. The foods are different, right? And the content is scientifically the same. It's just that we don't enjoy it except it comes in certain forms. Okay? All right? And so we're going to talk about fat. In this particular case, fat's fat. although there's different types of fats, you're going to learn those. Then we have the carbs, we have the proteins. So this is what we're after. Here, beans, a lot of water here, and a lot of carbs. So if you enjoy beans, you eat black beans, you're going to get a lot of carbs. So if you're one of those people who watch the carbs, then you might not want to eat the black beans. Now, so we talk about you are what you eat. Your body is a machine. It is the power plant for being able to raise your hand so you can text someone. So your power plant, you want it to run well. You get it? It is the power plant that allows you to push the accelerator on your big gas guzzling truck when you're going down the highway. So your body is like the power plants and like the nuclear plants, the fossil fuel plants. So we have to put water, fat, and carbohydrate and proteins in this plant to keep it operating. And based on what we put in here, we operate very efficiently, or like the power plants today, less than 50% efficiency, you get it? We don't function very well. So that's why we think about what we eat and what we put in our bodies, because it does affect our performance. Got it? Not just physical, but mental, and we're going to go and you're going to see some of those. All right? So it's very important, again, that you watch what you eat in your body. Now, as I go through this, I am not trying to convince you to change your dietary habits. I am not trying to convince you whether or not you should be a certain size, large, small, in between. That is not my goal. Follow? We're just going to talk about this from the chemistry that's occurring in our bodies. All right? And we're going to talk about that chemistry more from a nutritional perspective than a pure science perspective. Okay? Important definitions. These are critical definitions, and these definitions will show up on my exam. They always do. Malnutrition is caused by a dietary lack in the proper mix of nutrients, even though the energy content of food eaten may be adequate. In other words, you can get enough energy to keep running your machine, but your nutritional balance isn't there for your machine to be highly efficient, okay? For things to click like they should click and operate like they should, all right? Follow, you have energy, but it's not nutritional energy, all right? So that's when we talk about malnutrition, meaning you do not have the proper balance of the nutrients, okay? That's key to this definition. When it comes to being undernourishment is experienced when the dietary calorie intake is insufficient to meet the metabolic needs of the body. In other words, you have fewer calorie intake for you to really function, okay? And that need is based on how we take care of this particular machine, okay? So just eating doesn't do it. It is the balance of the food content and other materials that you're going to learn about that works for malnutrition, malnutrition, and in terms of dealing with undernourished. You could be undernourished or you could be malnutrition, and they're different, they mean different things. Note this. Although, okay, there are cases of malnourished and undernourished people in the U.S., 69% of the population in the U.S. is said to be obese, and that's by a definition. The U.S. government has decided what the definition of obesity is, and so that's not really picking on anyone or anything. That's just a definition, okay? But that has been a sliding scale all over. Okay, and depending on where things are, and it shifts back and forth. But essentially the point here is that there are more obese people in the United States than there are undernourished people in the United States. And it said that obesity is approaching smoking as the number one cause of death in the United States. That's pretty alarming, okay? So the point there is that we have this machine, and it's like the fossil fuel plant. If it's not properly taken care of, then it breaks down, and that hurts us personally. So I want to be concerned. We want to be aware of issues of malnutrition. Again, it's the mix of malnutrition. Undernourished is you didn't get the proper substances for your body to operate efficiently. So let's examine what we're eating by way of food labels. We'll read the statements on the right side of the slide first, and we'll talk about the diagram. Processed foods in the U.S. must list nutritional information on their label. That is a requirement in the United States of America, that it must be listed on the label. So if you go in a supermarket or go in a store anywhere and they don't have this label, then you want to ask them where the label is. The places that tend to be exempt are like bake sales and flea markets are exempt, and of course Grandma's Kitchen is exempt from it. Okay, but there are talks and discussion, if you read articles, where bake sales and flea markets are coming under some scrutiny. People say, boy, it should have a nutritional value there. If it's Grandma's Kitchen, you just say it tastes good. That's it. That's it. That's what's on the label. Okay. These labels provide information regarding the micronutrient content, such as fat, carbs, and proteins. So you get a big picture of how many fats, carbs, and proteins are in the foods you're eating in the Snickers bars or whatever you like to eat. Information regarding the energy content, calories, as well as the concentration of vitamin minerals are also listed on the food. And this is what they look like. And you're going to see later that these packets have changed over time and probably will continue to evolve. But at the end of the day, it lists the total fats. And in this particular case, you have about 10% of the total fats. Of the total fats here, and then we have 5% saturated fat. Then we have the trans fats here. And saturated fats, you'll learn about that on some slides to come. But saturated fats means there are no double bonds. There are all single bonds in saturated fats. And then trans fats would be unsaturated fats, meaning they have double bonds. And you'll hear them talk about, trans fats and polyunsaturated fats. We'll show you what those are like too. Cholesterol, no cholesterol in this. Sodium, about 7% sodium, and total carbs is 13. Dietary fiber, which keeps you regular, 14%. And here we have sugar at 20%. And this is one of the changes in many of the labels. The total added sugar is there, and we'll see that on some slides to come. Then you have your protein content. Then below that you have your vitamins, vitamin D, calcium, iron, and potassium. And we'll learn in this lecture why these are necessary for functioning. So the bottom line is, in the United States, these labels are required, and it helps you to have an idea of what's on the label. Now, occasionally you'll hear on infomercials or you hear sales pitches and marketing pitches for a certain product to say, and people who are nutritionists will say, if you can't name it, if you can't say it, don't eat it. Well, there are lots of chemical terms that you cannot pronounce. Okay, that doesn't mean they're bad for you. Okay, so that's really, in my opinion, a scare tactic. Not being able to read it or pronounce it doesn't mean it's bad for you. So if you're in a supermarket and you see something that you can't pronounce or you don't know what it is, pull out your phone and Google it. Instead of alarmist, see, I can't say it, therefore it must be bad. Got it? Pull it up and Google it, folks. All right? And it'll tell you, all right, what's there. So that's important to know. Not being able to pronounce it doesn't mean it's bad for you. Now, a balance of the materials is important for balancing the operations of your body. That is important. And one of the areas here, sodium, for example, being high sodium, it's not healthy for some people. Sodium allows for transport across membranes and materials to be soluble in the body because it's ionic, and ions tend to be able to dissolve in certain phases, in particular aqueous phases in your body. And your body contains a lot of water. You'll see that in a little bit. All right. So in order to accommodate these changes, this understanding, the labels have been changing and they morph over time. So you could compare these two labels on your own leisure. Okay. But the bottom line is that the tables have been changing, the labels have been changing, and you notice here it'll tell you how many servings and things. Now notice there's 8 servings per container, a 2/3 cup. Who eats 2/3 of a cup? Nobody in the real world does. Okay, right? It's like, oh, your problem is you're too large a serving. No, the portions are too small. Anyway, you get it? So you have to be aware of that. Okay, that's what it's based upon, and you want to know that. And so all these things have been changing. Okay, amount per serving. So they tell you how many calories are there. And so in this case, only 72 in this particular label. It's 230. And they tell you about the added sugar. And added sugar means there's natural sugar in some of the materials that you get, and then they add a little bit more sugar. Why? Yeah, make you like it. Okay? And that works. A little more sugar, a little more salt, and yeah, in some restaurants, a little bit of pork fat. Okay? And you get excited. All right, so these are all the regulations in this part. I don't expect you to memorize these labels, but be aware that what the purpose of the label is. Okay? I don't expect you to memorize these labels. That would be. So what is the composition of the human body? Well, that's important to understand. Look, you're mostly water. 56% water, 21% proteins, you have 15% fats, then you have minerals, carbs, and vitamins. This is what your body makes up. So you really are water. Okay, 56%, over half of what makes you is water. Human body consists mainly of water, followed by proteins and fats. I expect you to at least know that trend and know that you're greater than 50% water. So I suggest you really look at this slide. Mineral, carbs, and vitamins only make up 8% of the total human body. On average, a 150-pound person will contain 90 pounds of water and 30 pounds of fat. So that gives you an idea of what's there. So about 30 pounds of fat. So there you go. So twice that size, then that gives you about 60 pounds of fat. Okay? All right, so there we go. Now, we talk about these fats, and fat is not a description of a person's condition. It is a description of the chemical compositions within the person. Properties of fats are greasy, slippery, soft, low melting, water-soluble solids. We all need them. We all need a certain portion of fats in our diet. That is just the way our metabolism runs best. Yes, I do know some dietitians, some diets say, no, you don't need them, or you have the carb diets or whatever, but you do need a balance of these materials because that is who you are. Water, proteins, fats, minerals, carbs, and vitamins. Okay? All right? Now, some of the dietitians are aware of this, and some of the people who market, the marketing people, are really aware of this, and so they market it this way. They say, that's why I need you to drink this water, and then I'm going to give you this protein shake, and then I'm going to give you this fats, and by the way, I need you to take the minerals because they are aware of this table, and they try to make sure they use that. Health dietitians and nutritionists tend to do a really good job of this, and they are better at describing this than I am. So we have these fats here. So we have butter, cheese, cream, whole milk, more fats, and certain meats and fish are loaded with them. All these products are from animal origin. So there's animal origin, and the animal origin has the fats in them. Margarine and other shorteners are evidence that fats can also be from vegetable origin. Oils, such as those obtained from olive, corn, and nuts, exhibit many of the properties of animal-based fats, but in a liquid form. There is your difference between animal fat and vegetable fat. Vegetable fat is in a liquid, is a liquid, and animal fat is a solid. It's a greasy solid. Vegetable fat is when grandma goes and takes a big chunk with her spoon and puts it in the skillet to fry your eggs. That's when grandma does it, right? When you do it with a little bit of margarine or olive oil, okay? So the fats are greasy solids and the oils are liquid. Molecules, fats, and oils are both triglycerides. You will want to note that statement, which contains 3 ester functional groups. You'll want to know both those facts. So we have what's called a triglyceride, which means tri-3. You've learned that already, right, in previous lectures. Tri means 3. So we have these 3 functional groups that come together on this one central molecule to give us this triglyceride, which is an ester. Note that. So triglycerides are esters. So here we talk about the types of lipids. Fats are triglycerides that are solids at room temperature, or oils are triglycerides that are liquid at room temperature. You'll want to know that. Triglycerides belong to the lipid family, a class of compounds that includes cholesterol. Cholesterol is a lipid. Okay, and steroids is also a lipid. They have different functional functions in the body, but they're both lipids. All right, and so there's a host of others that are there. So the triglycerides are formed from the reaction of fatty acids and an alcohol called glycerol, and we'll show you that on the next slide. Exactly what this structure looks like. But for now, let's take a look at the diagram on the left of this slide. Types of lipids. We have lipids, which can be broken down into triglycerides and other lipids. Beeswax and steroids are examples. But then triglycerides are fats and oils. You will want to know this diagram. And in fact, it's very likely you may see this exact diagram blocked out on the exam, and you'll have to fill in the missing boxes. Okay? So we have lipids that are what? Triglycerides and other lipids. And these are fats and oils. Now, for these fatty acids, this is what they look like in terms of their chemical structure. Okay? Fatty acids characterized by two features. It takes two features to be a fatty acid. One is a long chain, hydrocarbon chain. Hydrocarbon means hydrogen and carbon. And generally it's the even numbers, the 12s to 24, so you'd have 12, 14, 16, 18, 20, 24. It's typically what's there, and there's very good reasons for that. That's nature's template, and there's very good reasons for that. And you have a carboxylic group, which is a carboxylic acid at the end of the chain. So you have this carboxylic acid group at the end of the chain. So here, this author shows you three different pictures of the exact same thing. So these are all three the same. In the first diagram, we have this very, very long hydrocarbon chain, which is the fatty part of this molecule, and we have the acid part shown as COOH. And then he shows you in three different depictions here. One, this is hand-drawn line angle drawing, and this is a very, very popular one. Most chemists tend to draw it this way. This is when we put the ball and sticks together to make the molecular models. But they're all the same. What's the take-home point here? Fatty acids have long chains, hydrocarbons, and they have acid functionality. That's what makes them a fatty acid. So what do we do to get a triglyceride? So we have a fatty acid, right? Well, this fatty acid will form a new product, react with a triglycerol, with glycerol, which is actually a trialcohol. And when you react with this trialcohol, all three groups react, spits out water, which means there's a condensation reaction. But when it does that, it forms this triglyceride, which is a triester, shown in red in this particular diagram, in this particular slide. So the red area shows the ester functionality. Again, that functionality came from the reaction of a fatty acid. Fatty acid is a long chain hydrocarbon with an acid group. It reacts with glycerol, which is a trialcohol. Spits out water as the byproduct, which is healthy for your body, and produces these triglycerides. Okay, and here it's just shown in different depictions, in different structural formulas. Now, you've probably heard of saturated and polyunsaturated acids, and you hear them in commercials. Let's show you what that is. Saturated versus unsaturated. Saturated fatty acids contain only carbon-carbon single bonds. That's it. That means there are no double bonds. So you don't see double bonds in the structure. It's saturated. It is saturated when there are no double bonds. Okay? When the fatty acid has double bonds, it's unsaturated. And these can exist in cis or trans conformers. You'll have the trans, which means the two large groups on opposite sides of the double bond, or you have the cis, where the two large groups are on the same side of the double bond. And we name them, if there's only one double bond, we call it monounsaturated. If it's more than one double bond, we call it polyunsaturated, and I would expect you to know that. Okay? And so we have the polyunsaturated here of the linoleic acid here. Okay? And yeah. So you notice here you have linoleic acid and linolenic. They're different in terms of unsaturations here. Okay? You notice that? But they're similar. They belong in the same family. As a side note, these are precursors to the stale flavor in beer. Okay? So, Corona. Okay? That's why they put the lemon to absorb it. So, these are precursors that they produce the stale. And beer starts to go stale from the time it's made. That is just the nature of it. It starts to give out these aldehydes, and the aldehydes come from these carboxylic acids. So what about the carbs? Carbohydrates are compounds of carbon, hydrogen, and oxygen. The best known dietary carbohydrates are sugars like glucose and starch. They have a 2-to-1 ratio of hydrogen to oxygen, like water. Okay? So these again are the sugar and glucose. Sugars, glucose are the examples. Then we have monosaturated such as glucose and fructose. And they have a single ring. And the difference between them is alpha beta glucose arises from the position of the single hydroxyl group. In other words, if you take a look at the structure here of the first ring structure and the second where it say glucose and glucose, this is alpha. Note the C1 position. Tells you whether it's alpha or beta. If the OH is down, then it's alpha. If the OH is up, then it's beta. But notice here, essentially, when the alpha glucose has the 1 and 4 carbon on the same side. Okay? In the case of the beta, it has the 1, 4 on opposite sides of the ring, and that's what makes it so. Okay? So alpha is down in this structure, okay? And the 1 and 4 are both down, making it on the same side on the cis side, or syn, okay? In the beta, we have 4 down and 1 up. They're on the opposite sides in the trans, okay, configuration. And then we have beta fructose. Now, it is very likely you will see these structures on the exam. I highly recommend that you memorize them. It is very likely that I'm going to screenshot this first 2. They will be on there, and you'll have to identify alpha and beta. And depending on my mood, I'll probably move one to move them around so that force you to read them and look at them. Okay? But be aware of what alpha, notice 1 and 4, and beta, notice 1 and 4. So there are your carbs. By the way, this chapter involves an overview of the dietary chemistry. It is not an in-depth study of it. Yes.
Can you go back?
Yes, sure can. Oops.
So 1 and 4 are
Yep.
opposite sides on that one.
Yep. Notice here, the OH here. 1 and 4 on alpha on the same side. Here and here. See that group?
Yeah.
See this group? So that's what you want to circle in your notes. And then notice here on this one, you got this up, the OH up, and here we have the OH down.
So it's not like this side and this side, it's this side and this side?
Yeah,
Okay.
that's correct.
Okay.
That is correct. It's up and down, top and bottom. That's correct. Okay. So now that brings us to vitamins. So let's talk about these vitamins. Vitamins are defined by their properties. They are essential. This slide, by the way, is a slide you want to memorize. My questions on vitamins almost always come from this slide only. They almost look exactly like this word for word. I've been known to simply clip this, put it in, show up as true, false, and multiple choice questions. So let's talk about vitamins. Vitamins are defined by their properties. Okay. So vitamins are defined by their properties. They are essential in the diet, although required in very small amounts. You don't need much, you need a small amount. But they are necessary. We do need them in our bodies. They are all organic molecules with a wide range of physiological functions. In other words, the vitamins in there to help carry out a physiological function. Okay? That's what they're there for. They generally are not used as a source of energy. And keep that in mind. A lot of people say, I'm a little sluggish. Well, did you have your vitamins? Well, that might not be it. It may be that they didn't get enough food intake to burn the machine. You follow? And so you have to be aware of that. You say, well, you're on a strict diet. You can't have it. Then I understand that. Then you're probably got to live with being sluggish. Okay? But it's not like a vitamin. So taking more vitamin won't necessarily give you more energy. Although vitamins help break down the materials that give you energy. So there is your rationale for the vitamin. Okay? Some vitamins contain hydrocarbons and are fat soluble, whereas others have hydroxyl groups and are water soluble. It's a like. So in your body you have fat soluble domains and you have water soluble domains. And for order for the vitamin to function, it has to transport there. Okay, and it has to transport through either water or fat enriched domains. And designing the vitamin to transport to the sites is very, 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 very important. And that has to get into whether it's going to be fat soluble or water soluble vitamins. And the scientists who do this type of in-depth work understand those principles very, very well. Okay? So in this case, it shows you vitamin A is a lipid-soluble vitamin. Anytime you have these long chains, hydrocarbon chains, it's probably going to be a lipid-soluble. Vitamin C is a water-soluble vitamin. And you see that in terms of the ratio of oxygen to hydrogen. So when you have a higher rate, when you have more oxygens in the molecule, okay, essentially because you add more OH actually to the molecule, it tends to make it water soluble. When you have fewer OH groups in the molecule, it's more fat soluble, more hydrocarbons, more lipid soluble. So these are your vitamins. So don't forget, folks, take your vitamin. They're in small amounts, but they are necessary. What about minerals? Also, either ions or ionic compounds are essential to good health. They are very essential to good health. Okay? In the body, metal elements typically exist as cations, positive charge, and the non-metals usually occur as anions, negative charges. The important essential minerals are shown on this periodic table. Stare at this table a lot. My examples will come from it. So we have sodium, magnesium, potassium, calcium. We need these, but what? Too much is too much, right? Then we have phosphorus, okay, sulfur, and chlorine. These are really the micro minerals. Then we have these micro MIC minerals, iron, copper, and zinc. And we get these a lot in cereal, and that's why they'll say fortified with iron cereals. They don't announce that quite as much as they once did when the trend came on, okay? And some kids will do science experiments where they will they'll take like Total cereal and they extract the iron from it and compare the amount of iron in Total with some other cereal. And so they do this. And then we have these others. And all of these are very important. Then occasionally you'll hear about people will need lithium, and that lithium is to help balance other areas of their body. But these are the minerals that are essential and necessary for people to have in their body. And then there are others that doctors will prescribe to help with certain balances. And if you have to take those, that's your body firing, that's making the machine run a little better, go for it. This is not medical advice, but never be afraid to deal with those kinds of things. All right, it's chemistry, it's science, it is real. Okay. So what about this food energy? We get energy from food, but we don't always get this spontaneous burst of energy, except for caffeine. Okay? We get energy from food we eat, fats, carbs, and proteins. Fats, carbs, and proteins, and we learn to balance those according to our metabolic, how our body processes. The energy initially arrives on the earth as sunlight. You know this now, right? You know about photosynthesis, an endothermic reaction where carbon-based material, in this case carbon dioxide, plus water and chlorophyll as a catalyst to lower the activation energy to produce human life, in this case C6, carbon, hydrogen, oxygen species, plus oxygen itself. During respiration, the outcome from photosynthesis is reversed. So photosynthesis builds up the materials, and respiration burns it. So when we do respiration, we're burning, right? We're combusting. Notice here, good combustion gives us what? CO2 and water? Wow, that's what our body does. Our body knows how to process that and does a pretty good job of it. Glucose is converted into simple substance, carbon dioxide and water, and energy is released. And this energy is what lets you run across the campus. It's what keeps you awake in my class. Okay, that's energy. That's what it is. So this is what we burn. We burn when we burn our Snickers bars, or our Taco Bell, or our McDonald's, or our steaks. This is what we get. Okay. So let's look at these calorie requirements. Here's a take-home message in case I forget to mention it. There is generally speaking, there is a different dietary requirement based upon your age. That is the take-home message in this slide. That age is a part of determining how many calories you need, how much fuel you're going to put into your machine for it to properly operate. And we show you here, in this particular author, he divided it by anatomical females and anatomical males. So here, if you're anatomical females, from 14 to 50, you see the difference here. When the act turns into activity that you're going to be, if you're pretty active, you need a certain amount, okay? And it varies. But for the most part, you'd say that here for an active, it's going to look like it's around 2,000, okay? But what you hear people saying is that most anatomical females, 1,500, and they'll say most anatomical males about 2,000 or 2,200 tends to work. So, but it's different, okay, depending on it. But you notice here's not much of a difference. You got it? So just be aware of that there is, the answer on the quiz is yes, there is a difference. True or false? Yes, there is a difference between the calorie requirements based upon age. That is true. Okay? And we show you here, and anatomical females tend to require less than anatomical males. Okay? All right? So we got that? So what's the real cost of food production? Okay? When we talk about food production, we think about it in three broad categories: water, pollution, land. Okay? That's how this author chooses to do it, and many of the authors, when people talk about it, most talk about it in this fashion. Water, pumping water for irrigation depletes aquifers. Basically, if you're pumping too much water to irrigate, you could affect the natural water source. There is a place, I can't recall, somewhere in Asia, I think it was, where a company was pumping water and they affected the nomadic wells. Okay? So they were pumping to irrigate farms, and people were getting food and everything now, but the nomads, the people who lived off the land, their wells were depleting. Okay? So be aware of that. Rivers dry up. Okay? Okay? All right. pollution, waste from crops, livestock, insecticides, herbicides. This is what happens when we produce food. Land, erosion of topsoil, loss of forest cleared. So this is what happens. So there is an impact of us getting our vegetables, okay, our fruits, our nuts and berries, okay. It's never completely free when it comes to Mother Earth or to the environment. There is a cost. So we're concerned about that. We do our best to balance it. Be aware of this cost. What about the carbon footprint? Carbon footprint. Production of farming. Farming is 67% of the carbon footprint. That's huge, right? And that's because we need agriculture. We need it to sustain our way of life. Process and refrigeration's not that large. And all the others 12 years. So the largest impact on the carbon footprint is farming. That's your take-home message for this slide. Okay? Then we have transportation. Okay? So this is the impact of us being able to go to Myers and Walmarts and the other and Kroger's of the world to get our food. Okay? That we impact the environment in that fashion. So, what about the nitrogen footprint of food? And this is very important too, and this is impact again farming. The nitrogen cycle represents a set of chemical pathways whereby nitrogen moves through the biosphere. Okay, and then we show you all these plants. This statement is almost exactly like this in all my exams. It's a true and false. So you're looking at true and false, that first statement. It's exactly like this on all my exams. I don't even change it. Nitrogen-fixed bacteria convert nitrogen gas to ammonia. Ammonia dissolves in water. It converts ammonium. Ions, other reactive forms of nitrogen, such as nitrates, are formed via nitrification. Water break. And so, this is how nitrogen moves around the biosphere. So let's look at the diagram. So then we have nitrogen in the atmosphere, goes into the soil, bacteria consumes it, gets fixed here, and it just kind of goes here, and it goes back into the plants. Here it goes round to nitrogen, to ammonium, ions, nitrites, nitrates. They all go back in the soil, it goes in the plants, and then eventually it comes back out. This NOx and this N2O converts the nitrogen back into the air, and it continues around. And so what happens, if we overbalance the soil with artificial nitrogen, it throws the balance off. That's a take-home. And that happens with farming, when we over-farm or when we add too many fertilizers to it. Okay? We basically oversaturate the chemical balance, and it can't handle it. And there you have it, folks. You survived Chapter 11.